Okay, hello BC Calculus class. To stay on pace, we need to look at chapter 7.1 today. This is Monday, what's that, the 9th of January. So I'm on your textbook on page 317. Now, if you did not bring home your textbook, I have scanned this page and it will be shown as a PDF on this particular copy. So you should have that either in front of you or have the scanned copy in front of you while you do this work. Exploratory problems, set 7.1. Discover on your own or with your study group the property of exponential functions by working on a real-world problem. Yes, you're going to be working on this on your own in all likelihood. I'm going to hold your hand for a bit of it. I do want you to do this work on your own, though. So for number one, we talk about a function d, and it says this is 500 times 1.06 raised to the t power, and the description is the number of dollars in a savings account after t years given by this particular amount. They have a nice picture of it. We should enter that in on our calculator, mimicking the window that's in your textbook. Instead of d, we'll call it y1. We have 500 times 1.06 raised to, and we'll use the x power because we're in function mode with y's and x's. If you look at the window shown in the text, the number of years is across the bottom. I think if we go from -1 to 20, that should be about right for the independent variable. And if we look at the vertical scale, tick marks there every 500. I suspect if we sort of look at that carefully, we might say the minimum number of dollars is -200, and the maximum number of dollars is 2,000, it looks like, thereabouts. And the scale is every $500. And then if we hit graph, we get the picture that's mimicked in your text. Okay, so you should have that available. Now, once that's done, problem number one asks you to calculate the number of dollars at 10 years and at 20 years, and also at 0. Okay, so number of dollars at 0 years, which we can do without a calculator. That's simply 500 times 1.06 to the 0, and that's obviously 500. Okay, that would be our y-intercept if you're thinking xy. D at 10 years, well, I can't do that in my head, so I'll go to my calculator and work that out. I need to take 1.06 raised to the 10th power, multiply that times 500. I can do that easily over here in my home window. I could simply ask, what is vars, y vars, function y1 evaluated at 10? So that would give me the answer, $895.42. 424 if you want to round to the nearest thousandth. Note that you can also get that in the graphing window if you simply hit trace and then enter in 10. That gives you the amount without going through the home screen. Okay. And the third thing we were supposed to do for problem number one was find the number of dollars after 20 years. So we can do that same thing here in this window. If I simply hit trace and 20, that gives it to me at $1,603. And 0.5 around to the nearest thousandth. And yes, you should be rounding to the nearest thousandth for all approximations, right? 5, 6, 8. Okay, that's technically approximation there. This is exact. This is an approximation. Okay, so that's problem number one. For problem number two, it says calculate the derivative at 0, at 10, and at 20. And we can do those, pretty easily. Let me pull up the new screen. 500 is 1.06 raised to the t power. And the task is to find the derivative and then go ahead and evaluate it at 0. point, we're going to have to use our properties of derivatives of exponential functions. The 500 is a constant multiple. That stays there. Notice we still have 1.06 raised to the t power. That stays there. But we also include this natural log of the base, 1.06. So that's a constant multiple that's included into the derivative. Okay, so d prime of 0, easy to do. 500, notice that 1.06, 0 is just 1. We have a log of 1.06. That would be the exact answer. We can approximate it pretty easily a couple of ways. Again, go to your calculator. In the home screen, we could simply type in 500 natural log 1.06. That would 1.06. That would give us an approximation 29.134 to the nearest thousandth. We can also get that approximation in the graphing screen. Remember, the derivative is under the trace menu. This is option number 6, and we just plug in 0, and that gives us the same number, 29.134 to the nearest thousandth. And lastly, you can do this in the home screen. If you remember, Math 8 is often a convenient thing to use. So you type in the function, which we already have as y1, the variable that the function was defined as a function of x, and then the particular x value that we needed, which would be 0. Okay, so all those get the same approximation, at least to the nearest thousandth. You might want to look way out here at the end. There are some slight difference here, 10, 100,000, 10,000, 100,000, million, 10 million. At the 1 millionth place, they differ by 1 millionth. But for the approximation, they're the same to the nearest thousandth. Okay, so then we'll go ahead and do the same thing for 10. Since I'm in this screen, I can simply edit, change the 0 to 10, and hit enter. That gives me approximately 52.175, and then edit again, second enter, and then change the 20 or the 10 to 20. Okay, and so we get approximately, let me just take away my equal sign here and put approximately equal to 93.438, third decimal place. Okay, so that's number 2. By the way, go back to the graph screen just for a minute. There's another way you can get this off the graph, if you recall, and it's under the draw menu. So second program, draw, and if we draw the tangent line, number 5 is the tangent line option, and let me choose x is equal to 10 or 10 years in. What this does is it draws the tangent line, tells me the x value is 10, but also gives me the equation of the tangent line. And the equation of the tangent line is in mx plus b form. So you see y is equal to 52.175369975x, that's an x there, plus 373.670 and some change. Okay, remember the derivative is the slope of the tangent line, so you can see the same 52.175 appearing there as the slope of that tangent line. The other thing is this drawn tangent line is a drawing. The only way to clear it is to go back into the draw menu and choose option number 1, which is clear drawing. Okay. There is a question there you can answer. Does the rate increase, decrease, or stay the same as the amount in the account increases? You should be able to answer that. For number 3, let R of t be the instantaneous rate of change of money in dollars per dollar in the account. And you're supposed to calculate R of 0, R of 10, and R of 20. Okay, so let's see. R of t is the rate of change of the money in dollars per year. So that would be d prime of t divided by the amount of dollars in the account. So I'm going to divide that by D of T. Okay? So we know what each of these are. This was 500 times 1.06 to the T power times the natural log of 1.06. And dollars in the account was given as 500 times 1.06 to the T. And notice that this cleans up very nicely. This works out to be the natural log of 1.06, okay, because the 500s cancel and the exponentials cancel. Okay, so then it says to calculate this at R sub 0, R sub 10, and R of 20, and obviously these are all the same. It's the natural log of 1.06. If we go and just get an approximation for that, natural log 1.06, we see it's about 0.058. 0.058. 0.058. Okay, so that's working straight from here. You can also do this from the previous answers you had in problems number 1 and 2. So for example, if you wanted to work R of 10, you could take the D prime of 10 and the D of 10, and divide those two out. Using the approximation to the nearest thousandth, if we throw those in there, we'll get the following. Let's see. D of 10 was Y1 of 10. And if we divide that by the, oops, sorry, it's the other way around. It's the derivative divided by the function. So let me clear that off. The derivative was, let's see, math 8, right? Vars, y vars, function y1, comma x, comma 10. And we're going to divide that by the amount at 10, which is vars, y vars, y1 of 10. Okay, so if we divide those out, we get 0.058. Okay, same as we did up there. One thing you got to be a little careful of is if you work the individual, amounts. In fact, let me go up and write down the more accurate approximation here. 82689.082 and some change. Okay, so there's the natural log of 1.06. If we go in and looked at the approximations that we got for part 2, okay, so part 2 was the D prime of 10. So that was math 8, vars, y vars, function y1, comma x, comma 10. That was the approximation. We rounded that to 52.175, right? That was a rounded approximation. And then the amount at 10 was vars, y vars, y1 of 10. That was $895 and 0.424 rounded. And if we just divide those two rounded quantities now, 52.175 divided by 895.424, we get this, which is accurate. Let's see, 0.58268. It's accurate to 6 places, but it would be wrong out over here, right? I guess the point I'm trying to make here is that when you're looking for 3 decimal place accuracy in your final answer, rounding earlier components of the calculation can be dangerous. So you want to try to use the most accurate approximations that you can all the way through the string of calculations until you get to the end, and then round at the very, very end. Okay, so there we are. Okay, so that's part 3. Part 4 just tells you a little bit about percentages, and they ask you a question. Part 5 talks about y is directly proportional to x. Y is kx. K stands for a constant of proportionality. This was an Algebra 2 idea. Let me just remind you, if I said y is directly proportional to x and y is 10 if x is -3, find y if x is 4. So that's a typical, algebra problem. And the way you did that inevitably, or the way you should have done that, was start like this. Y is directly proportional to x, y equals kx. You put in some information. This allows you to find the constant of proportionality. Let's see, y is 15 when x is -3, so that's k times -3. So we divide through by -3. The constant of proportionality happens to be -5. That allows us to go back to our directly proportional equation. Y is going to be -5x, right, because k is -5. So then you can answer this question, find y if x is 4. -5 times 4, y of y is 20, or sorry, -20 when x is 4. Okay, so you can answer the question. What we're going to see in this particular exploratory problem is that if f is an exponential function, f is equal to a times b to the x, a and b are positive constants, then f prime of x is directly proportional to f of x. We did it in this specific case. Problem 5 asks you to prove that in the general case with a's and b's unspecified. And then problem 6 talks about prove that if f prime of x is directly proportional to f, then f is an exponential function, so you could try that as well. Okay, that's 7.1. If we're here Tuesday, then we'll work 7.2 in class. I would ask you to look at that ahead of time. There's a nice population problem on page 318. Once again, I'll scan that in for those that don't have their textbooks. Have fun. I'm sorry we didn't get as much snow as I had hoped, but that's life. Goodbye.